Okay, Le Châtelier's principle. Le Châtelier's principle says that when a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. In other words, a system at equilibrium tends to maintain that equilibrium. It bounces back when disturbed. I really identify with this chemical equilibrium here because I don't like it when things change. I resist the change, right? And so, you push this over here and I'm going to push it back, right? You do something, I'm going to undo it. And that's what a chemical reaction at equilibrium will do. It's going to come to equilibrium again. So again, if we're looking at this country analogy, this is Narnia and Middle Earth. He probably got in trouble with copyrights or something when he had that in his book before. So we have these two countries, and they have a fairly open border. People can go back and forth, right? If we have a population boom in Middle Earth, I don't know what happened. Sometimes, when there's a big snowstorm and power outage, then, 9 months later, a whole bunch of babies get born. Who knows? They didn't have anything else to do. So there's this big population boom here. Everybody's having babies. Well, it's getting crowded here. So what's going to happen when we add more people here? The rate of movement back to Narnia is going to increase. And so the rate of movement to Narnia will increase until we get back to an equilibrium. We've restored the balance. You could also think of it a little bit like a teeter-totter or, a boat, and you've got people on one side of the boat and people on the other side of the boat, and, you rock the boat a little bit, and it's like, no, you move back over there because we don't want the whole thing to tip over, right? So there's shifting to bring it back into balance.
Or they starve and die if there's no resources.
Well, I suppose that could happen, yes. No? So, if we look at this equilibrium, here we have N2O4 in equilibrium with NO2. The balance here is determined by the equilibrium constant. It's not equal concentrations, it's determined by the equilibrium constant. But it comes to a place where it satisfies that equilibrium constant. So before we mess with it, if we calculate what Q is, my pointer, there it is. If we calculate what Q is, Q will equal K. Remember, Q is the reaction quotient that's calculated using the equilibrium constant expression, but you can use concentrations at any time. They do not have to be at equilibrium. So now we're going to add some NO2 to this equilibrium. Well, we can write the expression for Q. Q equals NO2 squared over N2O4. So initially this was equal to Q was equal to K. If I increase this concentration, what does that do to the value of Q? It increases it. When Q is larger than K, the reaction will shift to the left towards the reactants. And it will keep shifting until Q is equal to K again. Because as the reaction shifts to the left, the concentration of NO2 goes down, the concentration of N2O4 goes up, and Q becomes closer and closer to K. Does that make sense? Maybe? Yeah, not convinced. Pictures. Same reaction, N2O4 and N2NO2. So here we've got our N2O4 and we have some NO2. It's at equilibrium. If we add some NO2, we're adding some of this product. Well, now there's more of the NO2 relative to the N2O4, and some of these are going to react and create more N2O4. The reaction, the system will shift to the left until equilibrium is reestablished. I like to think of it as, the chemical reaction is just kind of crotchety and grumpy. It's like, you put more NO2 in here. Well, I'll show you. I'm going to go this way and destroy your NO2. Right? Yeah. What if we add reactant? Well, it doesn't like that either. You cannot please this guy. He just wants to be left alone. Leave me alone. I've got it. Everything's good. Now you're sticking more N2O4 in here. Well, I'll get you. I'm going to react that and change it into NO2. We add more N2O4. At the beginning, at equilibrium, K equals Q. Q equals K. Remember, Q is NO2 squared over N2O4. So if we increase this number in the denominator, that makes Q smaller. When Q is smaller, the equilibrium shifts to the right. The reaction proceeds to make more products. Any questions? So here we have two examples. Here's our original equilibrium. These concentrations are not equal to each other, but they're level. As time passes, they're staying the same. And now we disturb this one by artificially increasing the NO2. So we're increasing this product. Well, that increase is going to react in the reverse, and it's going to form more N2O4. The N2O4 concentration is going to go up as the NO2 concentration goes down until they establish a new equilibrium where K and Q are the same again, and then it's just flat. We can do the opposite. We can take, we're at equilibrium, and we add a bunch of N2O4, and that's going to then decrease as it reacts, and it will cause the NO2 to increase. Again, they'll keep doing that until Q is equal to K once again. So you can push the equilibrium one direction or the other, but it's eventually going to get back to where it was. So this summary from the textbook may or may not be helpful. If you increase the concentration of the reactants, it causes the reaction to shift to the right. If you increase the concentration of the products, it causes the reaction to shift to the left. If you decrease the reactants, it goes to the left to make more. If you decrease the products, it goes to the right to replace what you took away. I think it's better to just think about how that equilibrium feels, right? You took away this, I'm going to make more to replace it. Well, how does it do that? So let's look at this equilibrium. We got 2 BRNO in equilibrium with 2 NO and BR2. What's the effect of adding additional BR2 to the reaction mixture? So we're going to add BR2. Is it happy about that? No. It wants to get rid of that. So it'll shift to the left. To the left. What's the effect of adding additional BRNO? Shift to the right. It's about the only dance move I can do. It's really pitiful. Does that make sense? Well, what about other things changing? If we have a gas or a gas mixture, then pressure and volume might be significant. The pressure and volume of a gas are inversely related. If you increase the pressure, the volume goes down. If you increase the pressure, the volume, no, I said that. You get the idea. So if the volume of a reaction mixture at equilibrium is changed, then the pressure changes. The system will shift to minimize the change. To simplify things, we're going to assume that these changes occur at constant temperature. Because the temperature can also change, but we're not going to go there. So here we have a reaction in a cylinder with a movable piston. It's a container whose volume can change. N2 plus 3H2 goes to 2NH3. Well, what happens if we push down on the piston? What happens to the volume?
Volume goes down.
Volume gets smaller, right? What happens to the pressure?
Goes up.
The pressure goes up, gets larger. So the equilibrium doesn't like that. You made my pressure bigger. I want to make it smaller. How can it make the pressure smaller? How many moles of gas are on this side? And how many on this side? So if the equilibrium shifts to the right, we're going to combine some of these so that we only have 2 moles of particles instead of 4, and that's going to cause the pressure to decrease. Because remember, the pressure volume of a gas doesn't depend on the mass of the gas. It's not dependent on the size of the individual particles. It's the number of the particles. So the pressure can be lowered by shifting to the right. Any questions about that? It's a little bit like maybe carpooling and traffic jams. Like when there's more pressure on the population because there's just so much congestion on the freeways, people are more likely to carpool because you take the same number of people, but you put them in fewer cars, things go better, right? It's kind of the same idea. What if we added helium gas to this? What would happen? What do you think? It will increase the pressure, the total pressure. What does it do to the partial pressures? It does nothing. Does nothing. Adding some other gas doesn't change the partial pressures of the gases that were already there. I got this one wrong in lecture one year. So adding helium, nothing happens. Question?
Yeah, where it says how the pressure will be lowered, it shifts right because there's more moles of reactants in the product.
Yes. It's going to shift to the right. That will lower the pressure because the reactants contain 4 moles of gas, whereas the product contains 2 moles of gas. So by going forward, we can get fewer particles.
And it would shift to the left if it was the other way around.
Yes, if we increase the volume, the pressure would decrease. It doesn't like that either. And so it'll shift towards the reactants to make more particles to restore the pressure that was there before.
Well, I meant if the chemical reaction had more moles on the right, then it would shift left.
Yes, yeah. It will shift in the direction of smaller moles of gas. And the reason that the partial pressures of these gases is important is because what does Kp equal? Kp is the pressure of NH3 squared divided by the pressure of N2 times the pressure of H2 cubed. Do you see a total pressure in there anywhere? It's the relation between the partial pressures.
So if you added a reactive gas, like some not a noble gas like helium, then you're dealing with a different reaction, it's a different problem at that point.
Yeah, if you added something that reacted with one of these things, then you've got a whole nother scenario. But if you added oxygen and there wasn't any sparks, and it didn't cause another separate reaction, it also would not affect the equilibrium.
Why doesn't it shift right in the hydrogen? What is,
Because the equilibrium is dependent on the balance between the partial pressures of the gases involved in the reaction. And well, Kc is related to Kp by just gas constant and temperature, and so that's not going to change either. It's a little weird.
so the equilibrium is dependent on pressure and.
Well, this equilibrium is dependent on the pressures of the individual gases, the partial pressures. Changing the total pressure, by adding another gas is not going to change the partial pressures. I paused there because I thought I went somewhere bad, but I didn't. You might say, well, when we changed the volume, that changed the total pressure. But it also changed the partial pressures, right? Just adding an additional gas does not change the existing partial pressures, because gases are so small relative to the volume they occupy that their individual size doesn't matter. They act completely independently. Those of you who have taken Chem 1A with me know that I think about gases as being a bit like the state of Wyoming, where the population of Wyoming is roughly the same as Fresno without Clovis. The whole state. You can drive for miles at night and not even see a farm light. I mean, there's nobody there. They're all concentrated in, different places. But does the size of the people in that state matter? What if they were all 7 feet tall, 300-400 pounds, big, huge people? Would it matter? No. You think about a liquid, like maybe we're a liquid in this class, or maybe people in an elevator. That elevator, I think, has a capacity of 10 people. Have you been in the elevator?
Yeah.
It's not very big. So if we had 10 cheerleaders or 10 of the offensive linemen in there, would we have a different experience? Yeah, because you get 10 of those big guys in there, and they might fit, but it's going to be squishy, and you're going to be in people's personal space, right? It's not going to be comfortable. So here, it's the partial pressure of the individual gas. So in Wyoming, if you throw a bunch of Canadians in there, do the people that are there even notice? No.
I'm sure.
Well, yeah, you can't take the analogies too far, but you get the idea, right? You get the idea.
I'm sorry, one question. How
That's
is that
okay.
different from this one then? So like when you're adding more here, it does shift?
So there we're changing the concentration of one of the substances.
Uh-huh.
So if we're adding helium gas, it's not one of the reactants or products. And so it is not changing the concentration or the pressure of the individual.
I think she thought it was
I thought I was
hydrogen,
thinking
correct?
hydrogen.
Okay.
Was helium.
Yeah,
That's why
that
I'm
would
so
be
confused.
extremely confusing. Yeah, so this is hydrogen and this is helium, and they are very similar, and they're even close to each other on the periodic table and all those sorts of things. But yeah, good. We cleared that one up. Anybody else? Mm-hmm.
For Kp in the denominator,
Mhm.
are you multiplying by P of nitrogen? Or is it like,
Okay, so I wrote H2. I just realized. It's P H2. Yeah. Brain fart. Yeah, it's the partial pressure of nitrogen times the partial pressure of hydrogen cubed in the denominator. Thanks for catching that. Anybody else? So here are pictures for this. So when we increase the pressure by decreasing the volume, that's going to increase the partial pressure of all of these things. And we could stick numbers into the equilibrium expression if we wanted to and show how that happens. But I think intuitively it does make sense that if things are more crowded, now we want to go to fewer particles, right? Because that's going to reduce the pressure. And that shift is changing the partial pressures. If we increase the volume, decrease the pressure, it's going to shift the other way. Adding the inert gas and how that doesn't affect anything is much harder to understand. So summary of volume change. Decreasing the volume causes the reaction to shift in the direction that has fewer moles of gas particles. Increasing the volume causes it to shift to the side that has greater moles. If there's an equal number of moles of gas on each side, then changing the volume is not going to affect the equilibrium at all. And adding an inert gas at a fixed volume has no effect. It doesn't change the partial pressures of the reactants and products.
And if it's like a fixed container and you heat it up, it does the same thing as increasing
We
the
will
pressure.
talk about temperature in a minute. Yeah. So the effect of a volume change, consider the following reaction in chemical equilibrium. What's the effect of decreasing the volume of the reaction mixture? So if I decrease the volume, that increases the pressure, and it wants to reduce the pressure. And go to the right. If we increase the volume, that decreases the pressure. It's not happy about that either. It wants to restore the pressure, so it'll shift the other direction. So temperature. If the temperature of a system at equilibrium is changed, the system will change to minimize, will shift to change. It looks easy to read. If the temperature of a system at equilibrium is changed, the system will shift to minimize that change. So here we are thinking mostly about exothermic and endothermic reactions. If we're thinking about gases, and we increase the temperature of the gas mixture at the same volume, that would increase the pressure, right? And so that would have the same effect as decreasing the volume. So we can think of heat as being a reactant or a product. And here we're going to assume that we're adding or removing heat at constant pressure, because we can make simplifying assumptions like that. So in an exothermic reaction, remember, heat is given off. Exo means going out. Exit. Heat is like money. Energy is like money. And the energy is leaving your wallet. Right? It's going out. Endothermic, endo like into, it's coming into your wallet. So heat is going into. Okay? So if we have an exothermic reaction, we can think of heat as one of the products. When the reaction proceeds, it produces heat, right? That's a product. So if we heat up the exothermic reaction, that's like adding a product. That's going to cause the reaction to shift to the left. One thing that makes this a little more complicated is that changing the temperature also changes the equilibrium constant. Yeah. Because, in the real world, there's multiple variables, and you don't get to pick which ones choose. They tend to all change however they like. That's one of the things that makes doing research on humans extremely difficult, is because there are so many uncontrollable variables. That, and then, there's ethical considerations of what's okay to do to people. Lowering the temperature of an exothermic reaction. Well, heat is a product for an exothermic reaction. If you remove heat, the reaction is going to shift to make more. The effect on an endothermic reaction is the opposite, because here heat is a reactant. If I add heat, it's going to make the reaction go forward. If I remove heat, it's going to make the reaction go to the reverse. Yes?
I'm kind of confused, because like, wouldn't increasing the pressure also change the equilibrium constant?
Increasing the pressure does not change the equilibrium constant.
Well, it would, because it would also increase the temperature.
If the temperature changed, the constant would change. The equilibrium constant is dependent on temperature. It does not change with pressure. The equilibrium will shift because of the pressure, but the constant is the same. When you
never have a system that has constant temperature. So if you increase the pressure, the temperature will go up.
unless you control the temperature.
Right.
Yeah. Yeah, so, I mean, working with systems like this is tricky, right? Because if you don't want to deal with the consequences of the temperature change, then you have to control the temperature in some way. The simplest way to control it is to have a really big ice bath and have your reaction mixture submerged in the ice bath. Because then whatever's happening in there, it will soon return to that same temperature. Or you can use, fancy electronics and heaters and coolers and stuff. So if we remove the heat, the reaction shifts to the left, and that results in the equilibrium constant being smaller. Here it shifts to the right, and the equilibrium constant gets bigger, as opposite for the exothermic reaction. So this is a cool demonstration that I wish I could do for you, but it requires having liquid nitrogen, which we don't always have. So this is a glass tube containing N2O4 and NO2. It's in equilibrium, and this is an endothermic reaction as written here. And so if we take this tube and we chill it, and that is minus 75 degrees Celsius. I tried it in an ice bath just to see if it would work. Nah, it doesn't work. If we chill it to a cold temperature by removing a lot of heat, we cause the reaction to shift to the left, we reduce the equilibrium constant, and we see no color in the gas. We've got all N2O4. If we heat this up, we cause the equilibrium to shift to the right, and the gas in the tube turns brown just by heating it up. This tube is sealed. There's no opening anywhere. So you take that and you cool it down again, it turns colorless. You heat it up, it turns brown. Colorless, brown, very cool. Any questions?
What happens at room temperature?
At room temperature, it's brown. Because this is 26 degrees.
Okay.
Yeah. So summary effect of temperature change. For exothermic, increasing temperature, reaction shifts left, value of K decreases. I don't think there's any benefit in trying to memorize a slide like that, because there's too many pieces, right? I think it's better to find something in your head that makes it make sense. Whether you're talking about people carpooling or just undoing a change, whatever makes sense to you. That way you get a problem like this and you can just reason it out. The following reaction is exothermic. What's the effect of increasing the temperature of the reaction? Well, the first thing I would do when given a problem like this is I would put heat into the equation. So exothermic, should I put heat as a reactant or a product? A product. So plus heat. So increasing the temperature is adding heat. Adding product makes it go to the left, right? To the left, correct? What about decreasing? Decreasing the temperature means I'm taking heat away, and it's going to shift to the right. Consider the exothermic reaction 2NO plus Cl2 going to 2NOCl. Which change causes a reaction mixture at equilibrium to shift to the right? Is adding more NOCl going to cause it to shift to the right? No. How about increasing the volume at a constant temperature? Well, these are gases, and that's a gas. So on the left side, I have 3 moles of gas, and on the right side, I have 2 moles of gas. If I increase the volume, the pressure goes down, and it tries to replace that to increase the pressure, and it'll shift to the left. Increasing the temperature of the reaction vessel. Actually, no. It's none of the above. Oh, I thought you said increasing the temperature.
No.
Oh, it has exothermic there. No,